That last video lets us state the following. We've already remarked that if one space is contained in another space, so H is a subset of V, then the dimension of H is less than or equal to the dimension of V. We can now go further. The dimension of H is strictly less than the dimension of V, unless these two vector spaces are actually the same. And this proof is so quick, there's no harm in giving it. Suppose the dimension of H equals the dimension of V, but H is not equal to V. So you've got some basis of H. Well, if this basis of H were also a basis of V, then H would equal V. So this basis of H is not a basis of V. On the other hand, H is contained in V. So these vectors are a linearly independent set contained in V that are not a basis of V. And according to the theorem we saw in the last video, we can make this a basis by adding vectors. Well, if we make this a basis by adding vectors, then of course this basis has more than n vectors. So the basis we end up with has more than n elements. We started with n, and then we added some more. This is a contradiction. We assumed up here that the dimension of H and the dimension of V are equal, and H has a dimension of n. Therefore, our assumption that H is not equal to V must have been false.